So we are going to start a Turing machine. In this lecture, we are going to see a Turing machine which act as a transducer. Okay. So before understanding this, you have to understand that Turing machine can act in two ways. One is it can act as an acceptor, and it can act as a transducer. Okay. What is acceptor is, for example, if you give one input string, okay, and from any language to the Turing machine, then acceptor will, when Turing machine act as an acceptor, it will take that input string, okay, and it will say whether that input string is present in the language or not, yes or no. Okay, so if it is not present, then it will say no. If it is present, then it will say yes. That's why it is called an acceptor. Okay, so if it accepts the string, then it will say yes. If it rejects, then it will say no. Okay, that is why it is called acceptor. Now Turing machine can also act as a transducer also. What transducer means? That when you give any input string, okay, to the Turing machine, it will not say that input string is present or not. It will directly produce an output string. Okay, that is what this transducer means. Okay, you give an input string, it will do some computation, okay, and produce a output string in that particular tape itself. See, this is a tape. Okay, in this tape you had given one input string a, b, b, a. Okay, and within this tape itself only, it will do some computation and it will produce this output within that tape itself. Okay, so you can see this red color, b, a, b, b, like this, right? So within that tape itself, it will produce an output. So that is how it will act as a transducer. Okay, and this Turing machine, the tape it is using is infinite tape. Okay, so don't forget all those things. So we will see the theory part. So this is what it is written in a theory also. In context of Turing machine, a transducer is a machine that takes an input string and transforms it into an output string. Okay, so exactly what I said. Unlike a decider, see what is decider means, I have the second name for acceptor also. Okay, so we can call it as an acceptor or decider. Okay, both the way it is. Okay, so unlike a decider or unlike an acceptor which determines if a language contains a given string, a transducer computes a function that maps an input string to an output string. So you can call that this Turing machine will act like a function. Okay, we learned all those things during your college time, right? So function is, what does function does? You give any input string, you give it any input, right, and it will do the computation. For example, the function is defined as f of x. So according to that f of x, it will do some computation and it will produce an output. So Turing machine will act like a function at that particular input string. So essentially it acts as a calculator. What does our calculator does? Exactly, we give some input string, it will, for example, 3 plus 5. So what does it does? Turing machine will give the answer for 3 plus 5, whatever the answer is, 8. It will evaluate and give you. So that is how Turing machine will act. It acts as a function, right? Now the next point is that Turing machine is, when act as a transducer, it computes a function of f sigma star, which implies sigma star, where sigma is a machine's input alphabet. So what does it mean? Is this can be called as a mapping function or transition function for transducer. Okay, so what does it mean is that when you take an input string, for example, you're taking an input string, and that input string contains an alphabets a and b. Okay, so using an alphabets a and b, I taken one input string, okay, that may be a, b, b, a something. Okay, now I will produce some output. Okay, the Turing machine will compute something and it will produce some output, and that output should also contains alphabets of a and b only, right? It should not contain 0 or 1 or something. If your alphabet is you already declared that your alphabet is a and b, then output string should also be contains A and B. So you can manipulate it like B or A and B. So answer may be something else, but that alphabet which contains output, that should be sigma A and B only. It should not be like this. For example, if your output is like 0 1 1 0, no, because you had defined that your alphabet should be A and B. So how it is possible 0 1? Okay, that is not possible, right? But if you define that your alphabet is 0 1, then your input string should contain 0 1 and your output string should also contain 0 1. Okay, so according to what you defined during the transition function, that should be throughout the computation, that should be followed throughout your computation. Those alphabets should be followed in input string also and as well as in output string also. Okay. Now the next line is the machine takes an input string and through its computation produce an output string. Okay, that is what we learned in. Okay, now the next point is halt state. Okay, this is very important. Instead of having an accept and reject states like acceptor or decider, transducer has a single halt state. See, what does it mean that in transducer we don't have a final state. We know actually we don't need a final state. Okay, acceptor we had a final state. We had seen that. Okay, in our whenever we are computing Turing machine as an acceptor, we had a final state. Okay, so that string can accept it. Okay, and when the rejection happens in acceptor, it will halt in non-final state and it will reject the string. Now coming to transducer, we don't need any final state because we are not accepting any string. We are directly giving an input and we are producing an output inside a tape only wherever the input string is given. So we no need of final state. So remember this point, transducer don't need any final state. Okay, it will directly compute it and produce an output. Now the only thing you have to remember is when the string is not there or something is it will halt in a non-final state. That's it. You don't have to worry about it that something would be problematic. Whatever the input string it will give, it will halt in a non-final state and it will produce the output. That's it. Okay. Now the computational power of transducer are capable of more than just accepting or rejecting language. As I said, okay, it can do more than accepting and rejecting a language. It can perform a computations and transforms a data. Like I said here, it had taken A, B, A, B, B, A, then it computed something and it produced an output inside this tape itself. So unlike our acceptor, we just take an input string and say whether the string is present or not. It can do some computation also, arbitrary computation, arithmetic operations, many things it can do. Okay, so that's why its power, this is what the power of its computations, right? So hope you understood. Now let's see one example where a Turing machine will act as a transducer. Okay, the example is Turing machine to find a ones complement of a binary number. So to find a ones complement of a binary number, I hope everyone knows what is ones complement of a binary number. So I had taken one example. Okay, here the input string, I taken both the input string. Now in this input string, ones complement, what does it it starts with 0. You can see 0 0 1 1, and this is a infinite tape. Okay, this every infinite tape consists of multiple cells inside it. Okay, and there is a read write head. Always a read write head is pointing at one particular cell. It will point to one particular cell. So now consider your read write head is here. Okay, at the first symbol. Are you getting it? Now this read write head will move either in left direction or in right direction. Okay, and it will move one at a time in one cell. Okay, it can move to one cell one at a time. That's it, either in left direction or in right direction. Okay, now what is ones complement? I hope you all know all about all this concept. Now 1's complement means 0 become 1, 1 become 0. That's it. So when your read write head is pointing at 0, okay, it will read this 0 and it will make it 1. Okay, then it will move in right direction, right? Then it will read this 0 and it will make it 1. Then it will move in right direction again. It will make this 0, it will read this 1 and it will make it 0. Are you getting it? Then it will move in right direction, it will read this 1 and it will make it 0. Then whenever it hit the blank, okay, whenever it hit the blank, you can stop. Okay, there is no problem in it. You can directly stop, and whatever the output is produced, that will be directly displayed inside your tape. So the output produces 1100. So whenever you hit the blank, you stop and the output is saved inside your tape. Okay, so this is one way. Now when you hit this blank, you can stop here, but there is one more convention. Okay, you take this read write head and point to the position where it all started, right? This is just a convention, it's just a courtesy. If you want to stop here, you can stop here. Okay, the answer is already produced, but it's just a courtesy that take this read write head and point it to the starting position where it is started. Okay, so that it would be, it looks better. That's it, nothing else. Okay, so how can you do it? Take this read write head, cross all the zeros, cross all the ones, and whenever you hit the blank, see, when you hit the blank, okay, you are moving in left direction. When you hit the blank here, okay, stop here and turn in right direction, then stop. Okay, turn in right direction and stop. So your read write head will again point in this direction, this is where you all started, right? So this is just a courtesy, just a convention. If you want to stop here, you can stop here, otherwise you just point it. I will show the Turing machine in both the way. Okay, anyway, result is already produced, so you don't have to worry. Okay, let's see how to design a Turing machine. So you understood the logic, right? So using this logic, we will try to design a Turing machine. So how can you design a Turing machine is, okay, take this input string, okay. Now take an initial state Q node. Okay, so when you observe the example, I had taken an input string which start with 0. Okay, it may be possible that it may start with 1 also. So both the possibility you have to consider it. Okay, don't just take one input simple, it start with 0 and start directly convert into 1. No, you have to take care of both the possibility. It may happen that your input string start with 1. Okay, so both the cases you have to analyze it. So what happens? So what would be the transition? So whenever you're seeing a 0, okay, what you have to do it? You have to make it 1 and move in right direction. Okay, or it may be a case that you are looking at 1, your input string start with 1 for that also. So whenever you see a 1, you have to make it 0, right? So that also you have to mention. Whenever you see a 1, make it 0 and move in right direction. Okay, now you at Q1. So whenever you see 0 in this initial state only Q node, you will make it 1 and move in right direction. This is what we have done. Whenever you see 0, make it 1 and move in right direction. Okay, whenever you see 0, make it 1, move in right direction. And whenever you see 1, so whenever you see 1, see, for that also configuration is mentioned. Whenever you see 1, make it 0. Okay, this is 0, make it 0 and move in right direction, make it 0 and move in right direction. You keep on doing it unless and until you hit the blank. You can see here also you will make it 1. Okay, you will make it 1, this you will make it 0. Okay, and unless and until you hit the blank, you have to keep on doing it, and whenever you hit the blank, there would be a one more transition defined. So whenever you hit the blank, okay, you keep it as blank itself, you don't have to do, or and then you can move in left or right direction. In my case, I'm moving in left direction, and you can stop in one of the state which is a non-final state. So here itself your produces the Turing machine. So your produces the output. So your Turing machine has already produced an output and it is saved inside your infinite tape. So this is your Turing machine. So this is one part. Now I told you that for a convention you can take this read write head, okay, and move it to the starting position. So till here it is okay even if you done it, but if for courtesy, if you want to move your read write head to the first position, you have to make one more transition. That's it. From Q1 you have to cross all the zeros. Okay, so what I will do is, I hope you understood, I will create one more Turing machine. Okay, so here itself I will create one more Turing machine. Okay, whenever you see 0, whenever you see 0, make it as 1 and move in right direction. Whenever you see 1, make it 0 and move in right direction. Now whenever you hit the blank, make it blank and move in left direction. Okay, or turn in left direction. Now you are reached at Q1. Now what I said is, you have to take this read write hide and point it to the starting position as a courtesy or a convention. So what you have to do is, you have to cross all the zeros in the okay, whatever 0 you get in between, make it as 0 and move in left direction. Okay, or whenever you find any 1, okay, make it as 1 and move in left direction. Okay, then you will keep on doing it, and unless and until you hit the blank. You're moving in left direction, right? You're moving in left direction, you will cross all the zeros, you will cross all the ones, and when you hit the blank, okay, whenever you hit the blank, make it as blank and move in right direction. Okay, and here you will reach one state which is Q3 and stop. This will stop. So this both the Turing machine you can do it. Okay, both are correct. Whatever find is easy, you just draw it. Okay, so I hope you understood.